So you all go to Perth now. There's a limit for 50 people. We need to know by this morning how many people are going to the excursion. So if you want to go to the excursion, sign up. The excursion is free, the transportation, but you're stopping for dinner at the Salt Lake, which is a very nice Texas barbecue restaurant on the way back. You have to pay your own for dinner. And the Salt Lake does not take credit cards or checks. So if you expect to get food at the Salt Lake, bring cash. The other thing about the Salt Lake is that it doesn't sell alcohol, but you can bring your own. So if you want to grab a few beers ahead of time, you can take us to the Salt Lake. Don't mind. And the banquet is going to be on Wednesday evening. There's a charge of $15 for the banquet. There's a sign-up sheet on Friday. We need to know sometime by today. But it's not as urgent as the discussion that we need to know this morning, but we'd like to know if you participated on the banquet by today. And there's a charge that we need to collect. Okay, well, without further ado, let's start and let me introduce Victor Batyrev from the University of Tübingen in Germany. And he's going to be giving a series of lectures at a very long time. Yes. 1 hour. Yeah, leave 5 minutes at the end for questions.
So, I'd like to thank for the invitation, and I'm very apologizing that my notes appeared too late, and still they contains a lot of misprints and inaccuracy, but it's better maybe to have something than nothing. Oh, sorry. And I would be grateful for any remarks if you during the lectures and afterwards concerning notes, etc. So the purpose of my lecture will be just to extract some elementary combinatorial basis for many interesting topics. The topics they come from complex algebraic geometry, number theory, physics, and but the basis for is rather elementary and combinatorial. So I would like to explain this basis and then relation to all other stuff. So we start with So we start with the following object. So we take M just to be lattice. That means abelian group isomorphic to z to the power d. And and just a dual.
Can you write more thickly?
Is it
Blackboard.
Try pressing it harder and see if it works better.
Do you have a fresh pen?
Those are the pens we bought this morning.
Need some new ones.
Okay. So the dual lattice natural pairing between both of them, so just M and to Z. And after that, I would like to take a finite subset. It will be a finite subset in M, so the cardinality is infinity. So that means finitely many lattice points. So sometimes I would take the node by just V1, Vn. And starting from this object, I will construct some other combinatorial ones. Sorry, something strange. Should I press? Maybe that's some other. Is it okay? Green one. So I would denote by delta just the convex half A. Consider it in the vector space just real extension of the lattice M. So the usual assumption will be the following. So I will assume that A generate a vector space, the lattice tensored by R, and in this situation, I have this lattice polytope. In fact, the dimension for this lattice polytope could be only in either D, maximum dimension, or D minus 1. So the special case, case is the case when a dimension of the polytope is D minus 1. And this, and moreover, I will consider this special case will be of particular interest is the following holds. If there exists a vector in the dual lattice such that the scalar product of Vi with this vector is 1 for all I from 1 to n. So this is a special case. We call this special case also a regular case. That means, geometrically, that means that all vectors they are lying on the one affine hyperplane with this equation equals 1. Otherwise, if it's not satisfied, we say about general case. So let me also stress one thing. So the general case in dimension equals D can be reduced to regular case in dimension D equals dimension D plus 1. So we can from a polytope of d-dimensional general case, and general that means D is d-dimensional. So we can construct another polytope. Let me then probably. Oh no. So the construction looks as follows. So from the lattice M, we go to a lattice of rank 1 more, just adding first summand, and we get dual lattice, and we have also canonical pairings from these extended lattices to Z. Now, if you have a polytope delta just in MR, it defines a polytope delta tilde, just the convex hull of 1 times delta n0. Sorry, one name, just one delta. So we can put. So if you have a polytope, like for example, simply on just a segment, we can put this segment just on the and here we have so in one dimension more, and here we have a polytope. So that's important, and of course you can go the opposite direction. So if you have a regular case dimension, oh, thank you very much. Dimension equals D. It is general dimension equals D minus 1. Then you, if you have polytope, and you can just restrict on this affine hyperplane where it goes, and you drop dimension one less. So these are first basic combinatorial object that I will consider. And now the object to study actually not combinatorics, but some algebraic geometry objects related to combinatorics. So main will be a polynomial. I will take a Laurent polynomial summation over lattice points in the set A. Here I write am x of m. So it's a Laurent polynomial. I interpret a lattice point in A as power for monomials. I take coefficients a, n in some field k. I fix base field, and this is the Laurent polynomial. It can be considered as a regular function on algebraic torus, or it's an element of this ring, which is isomorphic to Laurent polynomial in D variables. So we can change different fields. So for example, we can take k to be, well, possibility. There will be complex number field, real number field, it could be finite field. And we can ask about interesting questions related to this object. And it is interesting. The main point of my talks will be just to see that answers about polynomials, they have some kind of common combinatorial basis, and that means this base allows to transmit ideas from one area to another area, and this is the most interesting, actually. So the first was done. So now the first property I would like to discuss is some kind of some open condition. So we consider f, as I said, we consider f this Laurent polynomial, sum of am x to the power m, and runs over a. But we don't consider only one polynomial. We consider a whole family of polynomials if we vary coefficients. So for us it will be very interesting what happens if we vary coefficients of this polynomial, and therefore so we can take two possibilities. So one possibility we just keep monomials, so we consider just a fine space of dimension over k, and then it parameterize all these coefficients. Or we can take even some larger fine space. We can take a fine space and just to the power number of lattice points in the polyhedron. So, as I said, delta polyhedron is a convex hull of A, but not necessarily all lattice points on the polyhedron appear as A points. So that means A is just a subset of delta intersected with M, and A contains all vertices. So A should contain vertices of delta. So this is just one it's finite set in between these two sets. So so we can consider as parameter space either this affine space or affine space of larger dimension, and we introduce the notion of non-degenerateness. So the notion of non-degenerateness looks as follows. So open condition. So for this open condition, we need just one more notation. So for any phase t theta in delta, we define another Laurent polynomial, just slice of the original one, when we take not all monomials that appear there, but only those that appear in the intersection at lattice points on the face. So again, am x to the power m. So this and the definition for that I next need the following. So we say f is is delta non-degenerate if for any phase the system of polynomial equations. So I consider system polynomial theta f von theta. And then all logarithmic partial derivatives. So in order to write down logarithmic partial derivative, I should probably take, definitely take a basis of the lattice. But so assume that we have taken already basis. So then we can write down logarithmic derivatives of this polynomial, put all of them to be 0, and ask that this system has no solution in algebraic torus. So I forgot probably to say that the lattice M, if we go to spectrum of this group algebra, we come to the torus, algebraic torus of dimension D over K, and we expect that this system has no solution in algebraic torus over arbitrary extension of field K. That means, for example, an algebraic closure of K. So this is a geometric condition, and it's an open condition. So this is a very important condition. So non-degenerate polynomial. So if we restrict this condition on this affine subspace, will be also open condition. Actually, it defines both open condition in both on the both spaces. So let me explain just an example of this open condition. So, yes. Which one? Oh, thank you. I will do.
Is there any way to keep the board from going all the way up?
Yeah, I would like to.
Maybe you can bring it down again and try and lift it with your hand instead of using the.
Okay. Was it? There's no stop, yeah?
Let it go down and then try and lift it up with your hand.
If I. So, I don't know. So I will go. Yes, of course. Then disappears.
There's no stop button. There's a button and down button.
Ah, this is it. So, okay.
Hey, somebody can stay there and press it up.
Okay. So, I hope. Let me take an example. One of my favorite example because it's of simplicity. We take just to be lattice points 1 and Z, and the corresponding polynomial f will be just usual classical polynomial, one variable polynomial. So the polytope delta in this case will be just segment 0n. And I ask, and the open condition that I mentioned means that for any phase of this polytope, the corresponding, so we have only actually three possibilities for phases. The whole interval, but also a vertex and another vertex. In order to keep condition that that Newton polytope of F, this means that so one condition is just the product of lowest and top coefficients should be non-zero, and another condition which appears just fx, so we should this system has no solution, means that no solution. That means there is no multiple root of this polynomial. So, and it's clear how to so that it's an open condition on these coefficients. We can take not the whole. We can keep first and last point and drop some points here. Will be the same kind of open condition, but with on less number of coefficients. If we don't take all these points and only to keep 0 and some of other points.
I thought your condition says for any subset of that.
Yes, for any phase.
Any phase?
Yeah, yeah.
The phase,
In this phase, either the polytope itself or two vertices. But maybe for vertices, I should only to say the condition is that coefficient of the polynomial appearing to a vertex should be always non-zero. Otherwise, we can make our set less. So that means I should write down probably is one open condition, and for any phase of dimension at least one, because if you take the phase of dimension 0, there is nothing, no condition. So I can so this is a condition of non-degeneracy. Now I would like to express this condition in some geometric terms. This use a little bit toric geometry. Toric geometry suggests the following. So we take a compactification of algebraic torus to some toric variety with respect to polytope. So this compactification is easy to define in the case. If we assume that vectors, just a set of vectors, and assume that vectors vi minus v1 so that means I from 2 to n, they generate lattice M. So of course it's not necessary, but assume that it satisfies. Then the toric variety can be defined as a result of compactification under embedding of torus to projective space of dimension. In this case, it will be n minus 1, and the embedding is just by the following. So we would take a point here and associate with this point just point in projective space x to the power. So under this condition, so we would take monomials as just regular function, take embedding of torus, and take a closure. So the closure under this embedding, of course, it depends on this embedding. So it will be our toric variety. In general, in order to describe this toric compactification, in general, it's more common to write it in the form we write down projective variety as approach of some graded algebra associated with the polytope delta. So the graded algebra is obtained as follows. So we take a cone in the space of one dimension more, as explained. So the cone is generated by vectors 1, v1, 1, vn. So we take a cone. And we consider the semigroup of lattice points in this cone. So now a semigroup and the addition, if we will write in multiplicative form, so we have a semigroup ring, and so if we take semigroup ring over, it's exactly our ring as delta. So maybe I would but explain this construction for this kind of set A. So we can so in this case vectors we have, there will be just vector 1 0 1. So we take a cone generated by 1 1 etc. So it will be just this kind of cone. dimension 2. And we have a natural grading of lattice point in this cone just by first coordinate. So first coordinate will be, for any lattice point, will be non-negative integer. So if we have just take O lattice point, so lattice point with fixed first coordinate will give a basis for the homogeneous component of this the corresponding graded ring. So if we take approach, we get toric compactification in general. So what is how it helps? It helps. Oh, there's nothing more. It helps to define non-generate condition in the following way. Geometrically, we can take a hypersurface in torus defined by condition f equals 0. But if we compactify torus to a toric variety, that I explained, will be automatically compactification of this hypersurface. And it's important that this toric compactification is an equivariant compactification. That means the whole variety will be union of strata of different dimension, and each stratum of this variety will be isomorphic to a torus of a so the whole toric variety can be I'll write in somehow. It's a union of tori of dimension equals to the dimension of the space on the set. So that so we have stratification by tori of different dimension. This tori will be actually orbits of torus action of the torus on this projective space. But then we can intersect this closed hypersurface with each orbit. So we define to be just intersection of this torus orbit with closed hypersurface. It will be a hypersurface in the torus of dimension defined by equation, exactly equation at f theta. And the open condition demands that all these hypersurfaces are smooth and of correct dimension, means smooth of codimension 1. So this is a geometric interpretation of non-degenerate condition. So probably one more example. If we take polytope not one-dimensional but two-dimensional, so example, we take a data just to be convex Hall of will be triangle convex Hall of 3 points 0, 0, 0, n and 0. Just like. So in this case, one can see that toric variety associated with this polytope is isomorphic to P2, embedded to by Veronese into n plus 1 half minus 1 in projective. Just by so we interpret all lattice points this polytope can be as define embedding Veronese embedding, and the open. So if you have a hypersurface f, it will be compactified to curve of degree n. And non-degeneracy condition means that this curve, first of all, this curve doesn't go to 3 torus invariant points. So this curve lies in P2, but doesn't touch these 3 points. And intersection with any coordinate line will be transversal. That means will be will give n distinct points for any condition if we put condition just zi equals 0, I 1, 2, or 0, it will be a line in P2. So and the curve is transversal with the corresponding line. Transversal. So this is an example, geometric example. Now I would like to go further and write down next interpretation of this open condition of non-generous condition. Next will be interpretation will be using commutative algebra. Actually, it comes from with polynomial f, we associate a polynomial in one more variable. So we define polynomial f0, f1, and fd. All these polynomials, they are in one component of degree 1 of our ring. So and here and this ring. And this ring here I consider as a subring of Laurent polynomial in one more variable. So x1 plus minus 1, xt plus minus 1. So as I said, I add one more rank 1 lattice, and this gives you. So how to define? So f0 is just a product f. So we have the polynomial f was a polynomial of d variables, but we add one more variable and multiply it. Polynomials fi, they will be just logarithmic derivatives of this first polynomial, I from 1 to d. So then we get a sequence of d plus 1 elements of the elements of degree 1 in the graded ring as delta, and another interpretation of non-generous condition is the following. So f is delta non-degenerate if and only if f0, f1, etc., d is a regular sequence in our graded ring as delta. So that means regular sequence. It means that fi multiplication with fi is a induced non-injective endomorphism of the model generated by, or as delta generated by I. Delta. So we can multiply this multiply all the elements in this model by fi. It gives endomorphism should be injective for all I greater than 0. So this is an interpretation in terms of commutative algebra. Is based on the fact actually that S delta is a Cohen-Macaulay ring and of dimension of crude dimension equals d plus 1. So
the way you define, they all share the factor x naught, right?
sorry?
They all have the factor x naught, right?
Yes. Probably I should again write down the picture. So for the case n, take our so take a segment take our cone over the centered segment, then in this case g equals 1, and we have two polynomials. First polynomial will be just x and the second will be just a logarithmic derivative of so x0 x. So all monomials that appear for both polynomials, this will be f0, f1, both will be divisible by x0. So this will be, and it's some kind of homogeneity condition. This is exactly what I said that they are living. So the divisibility by x0 is exactly the grading filtration on the ring as did. Yeah. Okay. Roughly speaking, it means the following. So you have a regular sequence. It's a ring called Cohomology. If in this ring, let's take a local ring, but here's not local, but you can take. If there is a regular sequence, a regularity I explained, whose length is exactly the dimension, cool dimensional. So we can look in Hodge on in Griffith's house, I guess also. It's, but I can explain it later, maybe more details. So now the next step will be just based on this commutative algebra interpretation and go to some a little bit maybe more complicated, but still another interpretation of non-degenerateness. So the regularity of a sequence, there is a standard way of expressing a regularity of a sequence using so-called Kazul complex. And I will explain what it means just in our situation. So we have a lattice n, and we have also a lattice n tilde, just z plus n, and we can and the lattice m and embedded. So we can interpret monomials in lattice n as one. So we can associate with any monomial x mu. Differential form, one differential form of the logarithmic differential form of this type. So, and that's it's the way how to interpret M or the complexification or some real extension of well in the over reals or okay. We can interpret this as a set of one forms. So this is tangent by k is canonically isomorphic to omega 1 with this of this torus. If we take a dual lattice, then it will be just vector fields on the.
Invariant differentials.
Sorry?
We mean invariant differentials.
Yes, invariant differential. Invariant differentials. Yeah.
Which is not what I said.
Yes. Let's say it's in one a tangent field in one. So, due to Lie algebra. So the Lie algebra of the torus will be canonically identified with n tensor k. So that means we can apply elements of n to function on the torus. So in particular to our function, and also so we have also the torus of dimension w plus 1. So the Lie algebra of next torus will be just n tilde. So now we can construct a Kazul complex. So it will be a complex. I will write it in the following form and then explain what that means. So it will be graded complex minus tensor exterior algebra of the n tilde. So this is, but let me explain what I mean. So it will be some sequence of S delta modules with boundary homomorphism. So it starts, maybe it's from this. So it starts from S delta, which is isomorphic to S delta, zero exterior product. So the exterior product is just over Z. And here we have called D plus 1, but it's with a shift of grading by O1, and it will be defined as delta minus 1 tensor first exterior power of, and so next will be D plus 1 D square minus 2. Here will be as delta minus 2, and here will be tensor second, etc. So, etc. Until we have here at the end D plus 1 of n, and here tensor, and shifted by D minus D. Degree will be shifted. So we have a complex differential will be depending on the polynomial f. So the important is we will get we want to construct a complex whose differential will be dependent. So if we take how to define differential in a standard way to write down, so if we take u1, u d plus 1 just basis of the lattice tilde, then we can write down differential, but it will be next blackboard. So unfortunately. Yes?
It might be something is to just leave one board down and erase halves of it. And then the other half would be down long enough for people to copy it. Just erase the left half and start working on it, and erase the right half.
Just
leave that as if we're in normal classroom.
okay. That's, I mean, right. I think that's good idea.
You can try this on the previous.
So the next, I promised to write down the differential. So differential actually is defined on generator of each module, and generators of for example, of S. We can write down the form 0, S plus 1. So where A, J just our basis, as I said, J from 1 to D plus 1. So the differential works forward, so it is alternating sum over J0 to S minus 1 to the power J, and here I write down derivative, so it means here will be ui j of polynomial f0, or I can write another f0 is will be k. And here I write u j standard I s. So this is so the theorem, also standard result from commutative algebra, is the following. So that regularity of a sequence that I define is equivalent that complex Kazul complex is acyclic except for degree I equals 0, and will be just a resolution of this module of this arctic module. So another way of expressing regularity condition is acyclicity of such a causal complex, and we get resolution of this in degree. So it will be exactly the H0 part of this complex causal complex. And I said the differential depends on the choice of original Laurent polynomial, because exactly here we have used f0, and f0 was f multiplied by x0. So we have this causal complex. So we also denote this ring by simply SF, to be Artin ring of. Now, next point is to determine, to use the notion of determinant of the complex to define. Sorry.
How does D act on the portion coming from S delta?
How do you,
You just told us how that.
so we know that each our elements of the module, they are of the causal complex, they are just stereo power of n times s, and this is a free model. So if we tensor by z, it will be a free S delta model. So it's enough to write down on generators. And generators I have written here.
Linear.
It's linear. It's S delta linear.
How does your partial F0
It acts actually on any polynomial. So we can say, but maybe it's better to explain explicitly. So Ji, or any element. Yeah, I write. So this will be just x0 and summation over m in A. And now I take just m x, and of course am. So this is action of any element of the lattice. Sorry, what I forgot to say. This is true. This is it's not quite. What the idea is here I use. U should be an element here, and then I don't need to write down here x0, because here will be will be 0.1 or 1m. So so the summation will be of course on here, but here will be just 1, just 1m. This is the action. Just logarithmic derivative was. So I interpret lattice point in the dual space as just as invariant vector field, logarithmic derivative, and apply this to this. That's all.
That's different from just multiplication by Fi, Fj.
This is not multiplication. It's just. Could you put again your question?
Well, I was just asking whether you would use this multiplication by this Fj.
You mean there is such an operation?
No, you define these FJs.
You have a sequence. F0, F1, F
I can take instead of maybe it's better in my notes. Instead of f0, I took just a polynomial, a little bit better polynomial, x0f minus 1. But all derivatives they disappear on this minus 1. But maybe it's better to write down not zero, just write down this polynomial, and then it will be no special preference for f0. But the action is just you have a Laurent polynomial. You can apply vector and then vector field, and the result you solve.
There should be a partial with respect.
I'm sorry. Here's not was a mistake in the notes that here shouldn't be wedge multiplications. So it will be, in the dual interpretation, it will be wedge multiplication. It's just like so. This is maybe the only little bit complicated, or it's not complicated. It's like tensor analysis, but tensor, no, not analysis, but tensor algebra. But we are forced to consider. Any questions concerning this?
This you survive as a logger.
Oh yes, we have here this element, and we delete it here, and here we. And we can see that if we define in such a way, it will be independent on the way how we write down. So it will be correct way. We can do some construct and the dual complex. Then will be some other differential related to wedge multiplication with d of f of differential of, but I don't need it at the moment. So we have such a complex, and then sorry? Yeah. Now I need the notion of determinant of a complex. It's a notion from homological algebra. Actually, some special situation. It's some notion which generalizes the determinant in the case of mapping of two vector spaces. So we consider R integral domain, and K will be a fraction field. So now I assume that I have a complex of R modules. So I have a complex of R modules of just one, etc. Complex which is exact after multiplication by tensor multiplication with K. So if we extend scalar to K, but it's a complex of R modules. And over K, it's exact. In this situation, one can canonically associate a fractional ideal in the field K. That means some kind of determinant of the complex will be a R module which is contained in K will be locally free of rank 1. So this is a notion I need, but I want to explain at least a definition how it can be defined. So the definition can be done by induction on length of the complex. So for complexes of length 1, it's a standard. So that means complexes as this. So in order to get exactness by tensoring with K, it means that these both will be modules of, I forgot to say, this complex of locally free modules. Also important, not arbitrary R modules, but locally free. And then we'll get here invertible model. So here tensor by K will be a vector spaces, and they should have the same dimension. So we take just the determinant of the, we take one basis here, we take one basis here, we take the determinant of the matrix, and this determinant is uniquely defined up to change of basis in both models. But change of basis, it's multiplication by matrix with a determinant invertible element of R. So that means determinant, or better to say, the ideal generated by determinant is uniquely defined. So determinant is not can be changed if we change the basis, but the ideal would generate it. And the more general, we do success by splitting. So we split, in more general, we split this term in two parts, S1 prime to prime. And we split in the form that the map on the projection of this to C0 will be isomorphism if we tensor by K. So that means, and now we define the determinant of the complex as, sorry? I forgot to say. Everything is enough to define in the case when all modules I said projective, but it's enough to consider even free modules because we can do it locally, localizing, and so we assume that. So in the yeah.
And locally this idea will try to trivial.
Which idea?
Excuse me, maybe you should start this in the afternoon.
Okay. So we take okay. I can explain. And so the determinant will be just the determinant of the complex truncated complex just by if we change and.
Wait till the afternoon. It's better to not rush.
No. Okay. Then.
No, go then. Okay, please stop.
Should I stop now?
Yes. Okay, so we don't have a break. There's no time. I have a couple of now. So there's a break after this talk. A long break, 12 minutes. And that break is going to be the last chance for you to sign up for the trip. Also, another announcement is that Charles Doran